you ready?
Yes.
Okay. So it's my pleasure to introduce Elijah Seay for his science seminar presentation. Elijah is a double major in math and physics, and he's also an accomplished member of the men's wrestling team. He's been nationally ranked as a wrestler for 3 years in a row and has gone to the national tournament twice. He actually traveled to the national tournament recently, and when they arrived, found out that he'd been called off because of the coronavirus. I first met Elijah when he took graph theory with me as a freshman, which is rather unusual, and I wasn't sure about a freshman taking graph theory because it's more of a junior level course. But he did incredibly well. He was one of the best students in the class. So last spring, I asked Elijah if he'd be willing to work on a research project with me in graph theory, Ramsey theory specifically. And we met all semester and made some really good progress on some things that actually sort of surprised me what we were able to do. We continued to work on that some last fall, and Elijah submitted an abstract and was able to present this as a poster at the undergraduate poster session at the big national math meetings in January. I think some of the talent that Elijah brings to the wrestling mat, he also exhibits as a mathematician. He's kind of quick and agile in a way, and that he's able to adjust quickly and he really thinks outside the box. He also has sort of an aggressive talent as a mathematician as well. I think he's willing to tackle a problem and take it head on, and he's not intimidated by it. So it's been a pleasure to work with him, not only for what we were able to accomplish, but his willingness to work on these problems and the effort that he put into them. So I'm proud of him for his work. He's planning to work on a graduate degree in mathematics. He's been accepted to West Virginia University for the fall. He's still trying to decide what he's going to do with that, but I know he's going to make a good name for himself in the future. So I hope you will enjoy hearing what he has to say. Thank you.
Thank you, Dr. Lindeman, for the introduction. Today we're going to be talking about Ramsey numbers for trees of large diameter. Now, as Dr. Lindeman said, this almost began freshman year with my interest in graph theory. So when we started talking about research topics, we actually didn't start with this, even though I already know I kind of liked graph theory. We went through Chinese remainder theorem and Euler numbers, plenty of other topics before we settled on researching Ramsey theory. So glad we did it. It was definitely a more interesting topic myself, at least. To begin, to give some historical context for it, Ramsey theory was actually discovered more or less on accident. Frank P. Ramsey was a British mathematician, philosopher, logician, was his main focus. He was actually writing a paper on formal logic, and his conjecture for that turned out to be wrong, but on his way he ended up discovering Ramsey theory as a minor limit for us. And luckily he did pursue that attempt to discover this field. Has some great applications and discoveries since then. Graph theory goes back to one of the first examples of real world situations was in Königsberg by Euler. He was a Swiss-born mathematician, and while he was in Königsberg, he posed the problem that if you started on any landmass, which in terms of graph theory would be a vertice and which would be an edge. So if you started on any vertice or landmass, if you could only cross one edge or one bridge once, could you come back to that point? And his conjecture was that you couldn't, and it turned out to be true. And that was one of the first introductions there in the 18th century of graph theory. Later on, we get to Ramsey theory here in the 20th century, and we end up with this definition. small symmetry T such that every two coloring of a K2, which is a complete graph, every vertice is connected to every other vertice through every edge possible. So it's just the biggest graph, more or less, you can get that amount of vertices. Contains either a red copy of graph G or a blue copy of graph H. And this is called the Ramsey number of G versus H. In the case we're going to talk about today, G and H are the same. This is called diagonal Ramsey theory. And it's just a relevant case. For the notation, it's not going to have two different graphs in there, it's just going to have one graph since they're equal. So the R of G equals 2. When trying to prove this, you end up with, when you have to prove T, you have to prove it doesn't exist in every two coloring for the case of T minus 1. So a complete graph of 1 less vertices. And for that, you'll need a counterexample because it's for every two coloring. It doesn't exist in 1. So the counterexample is fairly easy compared to when you prove the upper bound. You have to do a whole different situation of case analysis where you determine that the value is present in every two coloring, and considering the amount of configurations, it is much. In the beginning of Ramsey theory, there was classical Ramsey theory, which is just complete graphs versus complete graphs. And just to show the modern relevancy of it, there's only so many of these problems actually figured out, and the dashes or the slashes that look like fractions are just the balance of what the possibilities are between these Ramsey numbers. So for K3 versus K3, which is just a triangle versus a triangle, it's 6. But you go to K4 versus K4, you get 18, which is a decent bit larger. When you get to K5 versus K5, even today it's still unknown and has 6 different possibilities and it only has these bands. Paul Erdős, he was a more recent researcher in the field of Ramsey theory, one of the great minds in mathematics, well known. He had a quote on this showing how difficult this problem would actually be posed to be. Is if we had aliens come to Earth and ask us to solve a Ramsey number of K5 versus K5, if we got all great mathematicians in the world and all the great best computers and put them all together, it'll take us a year for we to have a chance to figure it out. If they all ask us to solve K6 versus K6, the only way to be able to be to retaliate first. So it seems pretty hopeless when you look at it that way of like how hard the problems can be. And just to show some figures to put in context, just for one of the possibilities, which is say Ramsey number was 45, K5 versus K5, there are 10 to 298 configurations of that complete graph being two-colored. And there are roughly 10 to the 80 atoms in the universe. So if you went through and programmed to go through every single option there, it would take quite a long time. Start off with a proof of classical Ramsey theory to introduce this before we go into the next class of my own, or of our own. I'm going to go through a classic problem called the party problem, and it proves the case of K3 versus K3. It can be represented as a triangle as well. So you have a group of 6 people, and you want to prove that there exists either a group of 3 strangers or a group of 3 friends. So to begin, you want to prove that for 5 people, there exists a case where there's not 3 people that are friends or strangers. And there's an example in the top right corner where each person in that group is represented by a vertice, and each edge is their relationship. So the person on top will be friends with that person down the left, and they're what we call C5s. They're cycles of 5 people, but there are no triangles in there of 3 people that exclusively know each other or don't know each other. So that was fairly easy. They just need some more counterexample. When you go through the other way, you have to start proving that 3 people do know each other. So you can take one of the people out of the group just randomly, and there are 5 relationships to those other 5 people. So you can say based off that there would have to be at least 3 friends or 3 strangers. So we can assume, without loss of generality, which you see that as well, W, that we can say there are 3 friends. It would be the same if we were saying 3 strangers. And there would be those 3 relationships. Then we would suppose one of those friends is friends with the other friend. And we would get a K3, a triangle. And we'd be done for the right case. But we have to suppose the opposite case to finish the proof, to show every 2 element is going to be case. And the other case is suppose they're not. And you will see that they're all strangers. You will form that blue triangle. And then you're done with your proof, and you're proving that the Ramsey number of K3 versus K3 is 6. So for the section of graphs that, the category of graphs that we study are called trees. Now, this is a very broad class of graphs, but by definition it is a connected acyclical graph. So connected means it has to, all the vertices have to have some point connecting them. So if you have these 2 vertices connected separately, that's an unconnected graph. So you would connect them. And acyclical means you can only have one path going from every point to another. So if you drew this here, this would be cyclical because you have multiple paths. So you can only have one path going from any point on the tree going to another. Similar to actual trees, if you go on one branch, you're only going to have one possible route through the branches to make it to any other point on the tree. A lot is unknown about these classes of graphs actually still. There's not even a general formula to know how many trees are out there for a specific n value of how many vertices in a tree. There's a few classes known actually on the ends of the spectrum. We have stars and paths, and those have been known for a while. But in the middle, we have a few graphs like blooms, which are a star, which is this graph here, and a path is just what you would imagine. It's just a long straight line of vertices tied together. So that class was only found in 2016, which shows that there's still a lot of research to be done within this class of graphs. And so far, the conjecture for this class, or for the whole class of trees, is only to be less than 2n times 2, which opens a lot of room for research for further classes. So when we initially started this research, we weren't even looking at the broad class we found. We were actually looking at a very small class of graphs in consideration where one of the paths was only limited to 2, and we had this other path extended to any value of n. Within the first month or so, it was roughly 2 months maybe, it was more or less done. We figured out that class, but we figured out that we could extend this by adding a whole other section to the other path by varying the value of the P2. So it's just expanding upon the knowledge that we started to gain and coming up with different cases, and eventually found that we had this much larger class that we ended up discovering. Now, diameter is basically the size of, or the span of the tree. So like how far you can span from any point to another. The smallest, largest path is the definition. So if you want to go and find the longest path within the graph, which is very easy for these because you just take the 2 endpoints of the graph, and you can see that it is n minus 2 because you count the edges in between. And for a path that doesn't have a singleton there, n minus 1. So it's the second largest diameter. And this class wasn't named before And so we came up with a notation using spider notation to define it. When we started studying the actual Ramsey number for this class of trees, we had 3 different categories for them. There was the option of R and S, one being odd, one being even. There was the option of R and S both being even and R and S both being odd. And we had to do a case analysis for each one differently and actually didn't quite come up with one for both odd. But this is an example of one of the cases where R is odd and S is even, just specifically valued 6 and 7. So it gives you a specific tree to look at and a good example proof to show the proving methods that we used. So for the lower bound, we have to prove that it doesn't exist in one of those copies. So you have a complete graph of 6 and a complete graph of 14 that are unconnected. This tree has 15 vertices, so it just physically can't exist without the number of vertices there. So then we can move on to the other side of the other color and have to make sure it doesn't exist in that. So we would go and look at the K6 14, which I've drawn up there. You'll see 6 vertices on top. They're all unconnected because this is the complement of this graph. So it has all the edges this graph does not. So all 6 points here are connected here, so they're not connected to each other, but they're connected to all 14 on the other side. So this is called a bipartite graph, and I can draw any edge between the top part of the graph and the bottom part. And as shown, you can only draw a majority of the graph, but you can't get that final point on either of that. Just if you choose to draw the path of 7 first, you can't get the final point on path of 6. If you draw the path of 6 first, you can't get that path of 7, you can only get path of 5. And we prove the lower bound. For the upper bound, you start off with 2 coloring a K21. And luckily for us in mathematics, we can go based off prior research results and just like any science field, and take a prior result such as C14, which is a cycle of 14 vertices, which is over there in the bottom right corner. This was found to be a Ramsey number of 20, which is less than 21, so we can assume that there exists a C14 without doubt in this. So without loss of generality, we assume it's red. And since there's 14 vertices in this graph, all you need is a singleton coming off of any point. So let's say we go from point x1 and draw a red edge to any of the other 7 points that exist. Then you would be able to say the P1 is there and count off 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, 7 on the other side. And you have your tree, in this case, of a red tree. But you're done for the red case, so otherwise you're going to look at the case for if every edge from here to the other 7 points can't be red, they're all blue. So you end up with a bipartite graph of a K714. And with that point you were missing in the case of 20 vertices, with 21 vertices, you end up with a large enough graph to show that it will have a blue copy of the spider from path 1, path 6, and path 7. And then we're done with that proof there, and we can say, therefore, the Ramsey number of this specific spider is 21. You can actually generalize this well, first off, we did this with path. We found out later this cycle notation was better for generalization. Because it gives us more options for where we can connect points within the graph. That becomes more relevant later. But you can actually generalize this proof itself by replacing a 6 and 7 with R and S, as long as R and S equal 13. Because 6 and 7 would equal 13, keep the same amount of vertices, and they would both be odd and even because R or S would either odd or even. So be within the same class and same amount of vertices, and you can generalize a slightly larger class of trees within this class that we improved. And this was built upon to prove the whole a generalized case for any value of R, B, I, and S, B, E. And that was more or less improving methods. And here are results. We ended up with both the cases where both were even and where at least one was even, so 1 was odd, 1 was even. Both were consistent with the same ranking number as a bad. But we came into the odd problem of when they're both odd, it actually is 1 less. And the generalized formula is up in the right for all trees within this group. Here's the formula for just that class of odd trees. We conjecture it's this because through small cases and quite a few of them, we could see the pattern showing it was going to be 1 less than past ranking number. So we didn't quite get a generalized proof, so we can't say for certain, but it is a fairly certain conjecture. And conclude that this is true and our result will be completely finished. And also we actually looked at other research like the Broom research. The ranking numbers of the small cases where say R was 1 would be consistent with a Broom. It would be identical to that. And we found those ranking numbers matched up with research done on Brooms. So our research was consistent with prior knowledge within the field. Just to show that the applications within graph theory, I know chemistry teachers here are much familiar with chemical and biological modeling using like organic chemistry, probably a few other fields within itself. Programming, it's very commonly used, and in general, it guarantees structure out of chaos because you take these large structures of just a mess of dots and lines, and you can say that this specific structure that you want is guaranteed to form out of that large mass. So I think that's a fairly cool application. But on the other hand, in the mathematics field, you have this debate between applied mathematics and pure mathematics. And more or less, this was a pursuit of pure mathematics. We had no intention in mind with how the research is going to be used. Our job is to figure out the problem, and someone later can come through and figure out if there's an application for it. And there's plenty of historical relevancy there with Boolean algebra. It was discovered in the 19th century, long before computers, by George Boole, a British mathematician. And it's the basis for computer language nowadays. In number theory, for centuries now, there have been many problems posed just for the sake of numbers and primes and patterns within them. There's no known application for them when they discover it. And that's just the fun part of mathematics. There's not necessarily an end goal in mind, but you can almost guarantee that it will be used at some point. And here are the references. Any questions?
Elijah, you said that it's not necessary for it to be applicable, but just based on what you've been showing us, at least in my mind, I could see a lot of engineering applications, at least in, I could think on top of my mind something like urban planning. When you talk about points and vertices and maybe a little bit more calculus in terms of optimizing stuff. But do you see that also in this particular theory being applied or becoming popular in areas of, urban planning, engineering, any kind of that sort?
Yeah, more or less, because I see like modeling within how urban planners have been using like biological models like fungi, where they spread out into almost like that chaotic structure of a complete graph, but then they form those structures because they're guaranteed to find something at a certain point. Because I could kind of see that being used in urban planning as well, where you spread out this complete graph over certain resources and guarantee that structure within it. So I definitely see it within it. I just don't know how to exactly apply it.
Or neuronal synapses and stuff like that, sort of a network of things spreading out from the center. Yeah.
Chris.
I was wondering, sort of in a different direction, that might involve some biology as well. I'm thinking for birds to fly, for airplanes to fly, and even for cars to go down the road, you want laminar flow. And it's often intrigued me as well that, and I don't know what modeling one would use, but if you take a bird's, we talk about a bird's brain being small, but yet you see a whole flock of birds that can fly together in a pattern. Has there been any sort of application of looking at bird patterns in flight, especially for a flock that would involve these Ramsey numbers? And if you see any sort of inlet there, because it is amazing that they don't bump into one another when they're in one of these big clusters that's going along in the sky, but somehow they don't.
I'm not sure. I'd be lying if I said I knew of any applications directly. I'm sure they're definitely out there. Like, it's a very large field, vast amount of papers published out there that I'm sure find one and find some sort of structure being found out of that. I'll definitely say there has to be one on like swallows, I believe it is, the ones that are in very large clusters, because that's more on the fields. That's more chaotic looking, guaranteed structure out of that possibly. As far as like you're saying, those birds are just trying to limit each other. I'm not quite sure.
They certainly don't want to bump into each other, and they end up not. With the brain that's a whole lot smaller than ours.
Oh yeah, they definitely just have that individual capacity not to just they do their own small jobs, in my opinion, I guess. Again, I'm really in graph theory application of it. That's definitely an interesting look to take on it, that it could be applied to that possibly.
I think someone might have had a question on the Zoom group.
Hi, this is Jonna Sutherland. Can you hear me?
Yes.
Great. Elijah, really good job. I was wondering, how do you see that number theory might be used to model, for example, social interactions for a virus outbreak?
Yeah, that would definitely be applied for graph theory. Is that what you meant, graph theory?
Yes.
Sorry, I confused. I threw number theory in there too, just as an example. But yeah, it could definitely be applied that because you saw I did a social modeling at the beginning for the classical Ramsey theory model, and it's definitely been used within pandemic modeling as well. With a lot of disease, like they definitely have analysts on the boards for disease control, where they will model the spread of these diseases. Probably definitely one's doing it right now with COVID-19 going around. So it's again, not quite sure the specific use in there, but it's definitely Ramsey theory is definitely used to show that there's probably definitely going to be some sort of structure within these social connections that would cause the disease to spread and whatnot along those lines.
Okay, thank you.
Can you show the table that you had of known Ramsey numbers? How long would it take you to show Ramsey numbers for set of 3 and 3?
For the which ones?
Like the sets of 3, that 6 that
Oh, 6? Oh,
Yeah.
that's actually exactly what I did here. Just
with the friends. Okay.
Group terminology and more, I guess, understandable,
Mm-hmm.
applicable situation would be able to apply to or relate to. So,
Mm-hmm.
yeah, that's the lower bound proof, and what I drew out on the board was actually the representation of upper bound.
Mm-hmm.
Could you repeat that historical premise about that bridge crossing again?
Oh, Königsberg? Yes.
Yeah.
It's just one of the first known uses of graph theory and modeling, a real world example. So it was done in the 18th century by Euler. And are you asking the specifics of that?
Yeah, I mean, you went through that, and I thought I got it, but maybe go ahead and go again on it and the premise of the problem that started all this.
Oh, yeah, it's not directly Ramsey theory necessarily.
Right.
It's just the beginning of graph theory. So
Right, right.
Brushed through a little too fast. But the premise was that these land masses are equivalent to vertices and the bridges are equivalent to edges. So if you start on one of these vertices, is it possible to get back to that same vertice if you cross one edge each time? And it was found not be true in this case. And that was because of the odd amount of bridges on connected to one vertices, because you can leave and come back, but then you have to leave again and you can't get back. So if that's the case, you cannot come back to the same point.
So it's solvable if the number of bridges were just even?
Yes.
Any other questions? Okay, thank you so much.